You can write code with perfect syntax and hit 100% test coverage. But even a codebase that looks spotless on the surface can resist every attempt to add a new feature. Technical hygiene, clean logic, is only half the battle. Designing a deep domain model requires mapping your software to the actual business it serves. When those two diverge, the code itself becomes a burden. Take the case of an engineering team inheriting a system for managing syndicated loans, complex agreements where multiple banks pool their money to fund billion-dollar projects. The team began with what seemed like a logical baseline. They modeled the financial world using standard objects, facilities for the overarching agreement, and loans for the individual payouts to the borrower. They built this structure on a superficial understanding of banking terms. When software architecture is treated as a purely technical exercise without aligning to the deep business logic, it creates a fragile illusion of stability. That illusion shattered when domain experts requested features that the code couldn't handle. The bankers explained that a lender's share in a specific loan payout often deviates from their original share in the facility due to independent negotiations. To force this rigid model to work, the team bolted on a patch, creating a loan adjustment object to manually override the hierarchy. This patch triggered secondary symptoms, persistent rounding inconsistencies. In a $100 million deal, a lost penny destroys all trust in the system. These ballooning special cases aren't just typical technical debt, they are distress signals from a shallow mental model. When adding a standard feature feels like fighting the system, the architecture is demanding a total restructuring of its mental model. The team finally realized the mistake after intensive collaboration with the domain experts. They discovered that loan participation shares can change independently of the original facility shares. This realization led to a new abstraction. The rigid vertical hierarchy dissolved, replaced by a circular share pie network. The impact was immediate. Since the share pie could be adjusted directly, the loan adjustment hack was deleted. The rounding errors vanished along with it. Reaching this point is often difficult for engineers. It's scary to rip out foundational code that technically works, and it's easy to get trapped by the time and effort already invested in the old way. The team survived this foundational surgery because of their discipline. Months of continuous minor refactoring had kept the codebase flexible enough to absorb a major change. A successful breakthrough eliminates the underlying complexity that allowed the bugs to exist in the first place. With the noise of the old architecture gone, the team noticed that crucial rules for fee payments and drawdowns were still hidden inside generic methods. The clarity of the share pie cascaded. It led directly to the discovery of an explicit transaction entity, making the hidden rules of the business visible in the code. This chart captures the value of refactoring. It isn't a smooth linear line, but a step function, where small improvements lead to a massive vertical jump. This spike accelerates the system's capability, happening exactly when most legacy projects buckle under their own weight. Establishing a deep domain model changes the trajectory of the project, turning a rigid liability into an asset that becomes easier to modify as it grows. These breakthroughs are events. They cannot be scheduled on a roadmap or forced through sheer effort, but you can build the conditions for them. It requires constant refactoring, deep collaboration with business experts, and a shared language that bridges the gap between the code and the real world. Developers should refuse to settle for software that merely works. By leaning into architectural friction, you ensure that when the opportunity for a breakthrough appears, you are ready to take it.